hopefully this will work. Okay, shall I start?
Please.
Thank you. Okay, so let me join the other speakers in thanking the organizers for putting together this wonderful meeting, and also to allow those of us that have teaching obligations to participate, even though one perhaps cannot be in every talk. But the talks that I have attended, I've enjoyed very much, and also the discussion sessions, and this mentoring program is something that should be applauded. So what I will talk about today is gauged two-form symmetries in six-dimensional superconformal field theories coupled to gravity. So that's a title with a lot of lingo in it. I will explain it as we go along. This is work done in collaboration with Andreas Brown in Durham and Paul Konstantin Öhlman in Uppsala, and also to some extent with a master student we had in Uppsala, Finn Bjarne Kohl, who is now in Münster. The motivation for this work, where we started, was the Swampland ideas, and in particular the question, the grand question of what kind of low energy effective theories that have a quantum gravity completion. And more in particular, if we have quantum field theories that look consistent, we know that not all of them can be coupled to quantum gravity, and the Swampland program is there to tell us which ones are good theories and which ones are bad. Now, as we've heard before in the conference, in order to make progress here, we need to be a bit more precise about what we do. And one road ahead is to use string compactifications and study quantum field theories that have a lot of symmetry. And this is the road that I will take in this talk. So what I will do is that I will study six-dimensional theories that have superconformal sectors and are embeddable into supergravity coming from type 2b or F theory compactifications. So let me motivate a bit why this is interesting. Well, so asking how a superconformal field theory can be coupled to quantum gravity is a way of addressing the Swampland program, but in a limited setting where we have a lot of control because of this superconformal symmetry. Also, these superconformal field theories, they are related to more general quantum field theories, in that often a quantum field theory will flow to a superconformal field theory through an RG flow. And in that way, these superconformal field theories can be used also to say something about quantum field theories. And this works up to dimension 6, because 6 is the largest dimensions where we can have this superconformal symmetry. In 6 dimensions, so if we restrict to the 6-dimensional case, where we have perhaps most control, then these superconformal field theories will be intrinsically strongly coupled, and they will contain tensionless strings. So they are very hard to study using conventional field theory techniques, but we can probe them and we can engineer them with string theory or F theory by constructing solutions where that one may call non-compactifications. So we put our theory on some particular background where these kind of superconformal field theories emerge. Now, this is something that we can do, but it requires this non-compact geometry. And the reason why we need non-compact is that we must decouple all kinds of scales. So we must also decouple the scale of gravity, and therefore we cannot have a compact scale, compact configuration. So then, to connect to gravity again, we want to explore how we can put together such superconformal field theories into some compact geometry. And the idea there is that these superconformal field theories will emerge at certain point in moduli space of this compactification as certain degeneracies appear, so in certain singular limits. And now, something that has been a key to understanding superconformal field theories and to classify superconformal field theories are symmetries of all kinds, and in particular global symmetries, because these are something that have the same properties in the IR and the UV. So it's something that we can probe and say and use to classify theories. And in 6 dimensions, there are a particular type of symmetry which is called a two-form symmetry. So this is an example of a higher form symmetry. And 6-dimensional superconformal field theories may have this type of symmetries, which are global and discrete. Now, in string theory, any symmetry would relate to the kind of geometry. So what we want to understand is how these global discrete two-form symmetries, well, first how they emerge in these non-compactifications where we get the SCFTs, and then what happens to them as we go to a compact geometry. So this is the topic of this talk. What is the fate of these global two-form symmetries as we take superconformal field theory sectors and stitch them together into some compact configuration in string theory? And what we will see is that this, or what we will find evidence for at least, is that this two-form symmetry is either broken or gauged. And what happens is related to certain lattice embeddings. So there will be an important charge lattice, which is related to these tensionless strings in the SCFT sectors. And depending on how that charge lattice is embedded in a lattice of curve lattice of the base of this computation, we will find that this two-form symmetry is either broken or gauged. And this, of course, agrees with the conjectured absence of global symmetries in quantum gravity, which then connects back to the Swampland program. And maybe, yes.
Oh, sorry. I can ask a very quick question. Are there any other discrete symmetries we might think about in the 6-dimensional form field theories? Are there zero-form discrete symmetries?
For sure, yes. So there are certainly other symmetries as well. So here I'm cherry picking this particular symmetry because we were interested in it, and that's the one that we have explored. But there are certainly other symmetries. So there are the ordinary zero-form symmetries that one can study, and there are also one-form symmetries that are important. So but this is not. I left it out of this talk in order to be a bit more focused.
Thanks.
But that's a very good comment. Yes. So in order to understand, so this is just exploring one particular property of these theories, and so in order to have a complete understanding of of how superconformal sectors can be emerged into some compact geometry, one would need to study also other effects, other kind of symmetries. So that was a rather long introduction to what I want to say today, but I thought I wanted to give you this general idea because there is a bit of, there are quite a lot of different things that we need to put together in order to work on this program, on this problem. And here is then the short outline for the rest of the talk. So what I will do first is that I will talk a bit about what these higher form symmetries are, because maybe this is not known to everyone in the audience, even though they have been around for quite some time now. And then I will focus on the 6-dimensional case. I will talk a bit about the non-compact SCFTs, how the two-form symmetries emerge there. So still only focusing on the two-form symmetries there. Then see what happens as we couple to gravity and draw some general conclusions of what kind of gauge two-form symmetries we could see in 6-dimensional supergravity. Then, depending on how much time I have, I will talk about some examples, and then I will conclude. And do please ask questions along the way. I might not see the chat as well, but because then I will be a bit distracted. But if you want to ask questions, do so. So what is a higher form symmetry? A high form symmetry is a symmetry that acts on extended objects, and the idea is that we model it on a normal symmetry, which is then called a zero form symmetry. So an ordinary symmetry is something where the charges are point-like and there is a one-form current associated to it. And given that current, we can construct a conserved charge. By the way, do you see my pointer when I do this?
Yes, absolutely.
Yes, good. Good. So now that we have these charges, we can exponentiate them to create operators. So we may just more abstractly think that for any manifold, so d minus one dimensional manifold, over which we can integrate then the Hodge dual of this one-form current in order to get some number, which would be the conserved charge. So associated to any such manifold, we can associate a topological operator. And these topological operators, they will encode the group law of the symmetry group of this ordinary symmetry. And furthermore, these topological operator will couple to local operators, which are then the particles of the theory, in such a way that if we have a particle which is charged under this group, then we can surround it with a sphere, and we can read off what the charge or the representation of the particle is under this group. This is what is written here. So the idea of a higher form symmetry is that we generalize this. So for an ordinary symmetry, we had a zero form symmetry and coupled to zero form operators. So now we change everywhere where it was a zero form to a p form. So we will have a p form symmetry. There will be, if this is a continuous symmetry, then there will be a p plus one form current. We can then, in the same way, integrate this current over a d minus, so the Hodge dual of that current over a d minus p plus one dimensional manifold. And we can look at topological operators associated to these manifolds. These topological operators will encode the group law of the group, and we can couple these topological operators via linking now to p-dimensional operators, which will then be our local operators. So if we have a one-form operators, then if we have a one-form symmetry, then this will couple to line operators like Wilson lines. And if we have a two-form symmetry, then they will couple to some surface operator. So in 6 dimensions, these kind of two-form symmetries can emerge. And one way of seeing that is by engineering them in type 2B and string theory. So the important objects to keep in mind here from the type 2B string theory, from the type 2B or F theory picture is that so what we do is that we take the theory and we put it on some two-dimensional space, which has some particular structure. So we want it to be non-compact, and we wanted to have some singularity, which is given by a subgroup of U2. Then we look at what happens if we put strings on these. We look at what kind of physics we get if we put the objects of the theory on top of this space. So in particular, in type 2B string theory, we have D3 branes, and we can let these D3 branes wrap around the cycles of this two-dimensional space. So 2 complex dimensions. So if then these D3 branes wrap on compact cycles, then these will appear as strings in the 6-dimensional theory. And the tension of these strings will be proportional to the volume of the cycle that they wrap. And the charge of the string will be given by the intersection of the curves that the string is wrapping. So this will give some pairing among the curves. Then, if we would wrap this D3 brane instead on a non-compact cycle, then this will not be a dynamical object in the 6-dimensional theory. It will instead be a defect, and which will then have infinite mass. So that's why it's not dynamical. In addition, we can have gauge and flavor groups coming from D7 branes. And in F theory, we can encode all of this in an elliptic fibration, where then this two-dimensional space would be the base of the elliptic fiber. Now, the strengths and the defects here, they will determine the two-form symmetry that we have in the six-dimensional theory. So the way that this works is that these strings that we have, they will couple to through the so if we do a dimensional reduction of the C4 flux of type 2b string, then we will see that this will give a coupling of the six-dimensional strings that we have to some two-form gauge fields, which are called BI. And there will be one such gauge field BI in every tensor multiplet of the six-dimensional theory. And they will then provide a symmetry, which is a two-form symmetry, which has the gauge group U1 to the R. So R here is the number of tensor multiplets. And then the strings that we have, the dynamical strings that we have in the theory, in the six-dimensional theory, which come from these G3 branes on compact curves, they will have charges under the symmetry, which are related to some charge lattice, I will call lambda S. And then the defects, they will have charges which are given by a dual lattice, which is called lambda S dual then. And what these are in the geometry is something that we will see in the examples that come later in the talk. So what will happen then is that if lambda S and lambda S dual are the same, so if we have a self-dual charge lattice, then this SCFT will have then all these dynamical strings will screen the effects, will screen the defects. And this means that the two-form symmetry will be partly broken. However, if there are some elements in the dual lattice that are not contained in the original lattice, then we will have a remnant two-form symmetry, which will be given by the discrete center of this group. So see the ZR here, quotiented by then what will be in lambda S, which is then given by this this bilinear form on of the compact curves. So there will be, for a six-dimensional superconformal field theory, there will be a two-form symmetry which is related to these lattices, the charge lattice of compact curves and the charge lattice of non-compact curves in the geometry. So this translates this existence of the two-form symmetry to a very geometrical question. I should also say that this symmetry group, the two-form symmetry, is also known as the defect group, and is related then to a choice of quantized background three-form flux, which will then be related to these two-form, would be the field strengths of these two-form Bs. How am I doing on time? Do I have 15 minutes left or something like that?
Oh, 20 minutes. You started late.
Very good, thank you. Okay, these six-dimensional SCFT sectors also emerge naturally in the modular space of six-dimensional supergravity. So the idea here is that if we compactify now on a compact two-dimensional space, type 2b string theory or F theory by an elliptic vibration over this, and then then this will be some space, and it will have some two cycles on it, and there will be an intersection lattice associated to how these two cycles intersect. So we can then wrap D3 branes on these two cycles. They are all compact, so these will all be massive strings in the six-dimensional supergravity. However, if we now let the volume of the cycles that they wrap go to 0, then we go to a singular limit of this geometry, and we will get tensionless strings. So there will be a way of, in the modular space of a supergravity, get these superconformal field theory sectors, which are then specified by some particular sublattice in the intersection lattice of the base that we have chosen to shrink. So going from the other end, then we can think of what we do then when we construct compact bases is that we put together in some singular limits such superconformal sectors in a way that would fit into this intersection lattice of the compact base. But now each going back to when we start with the compact base and then go to a singular limit, then each such SCFT sector in the singular limit has its own two-form symmetry, generically. But we know the global symmetries are absent in quantum gravity, so we need to explore what happens then to this two-form symmetry. And one thing that would be, and the two things that are then natural to explore is whether it's broken or whether it's gauged. Now, in general, for a six-dimensional supergravity, one can show that the string charge lattice of a base will be a self-dual. So this answers the question that there cannot indeed be any global two-form symmetries for a supergravity. But this does not exclude the case that a subgroup of this group could be gauged. And this would then happen at certain points in moduli space. And the idea then is that there will be points in moduli space where only some of the BPS strings are screening the symmetry, and others remain uncharged on some part of the symmetry. Okay, so the recipe then, if we want to explore what happens to two-form symmetries in supergravities, is that and the recipe that we want to explore is that we will start from type 2b string theory or F theory on some particular two-dimensional base. And this base will have some string lattice, some string charge lattice lambda b, which is given by the second cohomology of the base. And then we will choose a sublattice in this base. We'll choose a sublattice of this string charge lattice, which will correspond then to a superconformal field theory with some tensionless strings at some particular locus in moduli space. And then we determine the two-form symmetries of the SCFT sectors that we get. And this will give us the putative two-form symmetries that we could have in the theory. And then we will go back to the compact case and see whether there are some diagonal subgroup under which the strings remain invariant. So the idea to have in mind is that there will be some different SCFT sectors. They can have different two-form symmetries, and the question we ask is how these can work together, and if there is some part of these different two-form symmetries that can remain. So for this to happen, then we need. So first we had this. We had the charge lattice of the base, and then we had the charge lattice of the defects, and we need there to be an element in this lattice here, which is not included in the charge lattice of the strings. So what one can show is that this dual charge lattice of the string charge lattice. So the string charge lattice consists of is the lattice we get if that is. Now let me see. I should have perhaps put this formula down. So in the string charge lattice, we have forms that have charges which are given by linear combinations of the cycles that we have in the base with integer coefficients. In the dual lattice, we can have integer coefficients, but we can also allow for rational coefficients in this expansion in the base curves. So this means that this dual lattice can contain rational elements, and these rational elements will be such that so if there is such a rational element, then that will not be part of the lattice lambda s. But as we multiply the lattice by some integer, then we will get an element of lambda s. So these kind of elements, they live in what is known as a torsional subgroup of lambda b over lambda s. And this then is related to what number we need to multiply with. So we have some fractional elements, which should then be at the intersection of the rational charge lattice with the base charge lattice. And if there are such elements, so this is a lattice theoretic question, one can explore it. If there are such elements, then we could have a gauged two-form symmetry remaining. So the question we need to explore then is whether the lattice, the string charge lattice, is primitively or non-primitively embedded in the lattice of the compact base. Okay, so this brings me to some examples. So we have explored this in supergravity with 2,0 and 1,0 supersymmetry. 2,0 examples come from, so to get 2,0 supersymmetry, we need to compactify type 2B string on a Calabi-Yau twofold, so a K3 surface. And for these bases, the base, so this lattice lambda b, the lattice that determines all two cycles of the base, is given by in the most generic description by lambda 521. So this is always the case if we have 2,0 supersymmetry, and then if we have SCFT sectors, sorry, this is typo. If we have SCFT sectors here, then there will be a charge lattice associated to these, given by a sum over lattices associated to each SCFT sectors. And 2,0 SCFTs have charge lattices that are given by ADA root lattices. So lambda s here will be some sum of ADA root lattices. This means that the gauged two-form symmetry will be given by the torsional subgroup in this group here, in this lattice quotient here. So what we can do then is that we can explore this either in examples, as we have done in our paper, or we can try to classify it. And there are two ways that one can try to classify this. One can use lattice theoretic techniques, and there have been some nice papers over the past years studying heterotic complications on toroidal orbifolds, which have exactly the same kind of lattice governing them. So this is something that one should explore in more detail. Or if we choose a U-duality frame where this K3 surface has an elliptic fibration, then one can show that this group is in fact given by the torsional part of the model Weil group. So then one could classify these kind of configurations using their model Weil groups. And there is also a lot of literature on that over the past couple of years. So to look at an example, we can look at one of these elliptically fibered K3 surfaces. So then we can describe the system in terms of a Weierstrass model. So say we have our K3 surface given by this particular Weierstrass model here. Then we can we can read off the singularities we have, and we can use Kodaira's classification to see what kind of elliptic fibers we have. And we find that we have, in this case here, we have two type 3 fibers and one type 1 fiber. So there will be AD gauge group associated to this, and the centers of those will give us the global two-form symmetry of the SCFT sectors, which will be set. There will be set 2 and 4 of these for this setting. Then this particular model also has a torsional sector, which is given by, if you put in y equals to x equals 0 here, you can find that there is a torsional sector which has Z2 as its torsional part. So, and this then is the gauge two-form symmetry that survives in this compactification. Now, for these 2,0 theories, we can also explore this via duality. So we started here with some 6-dimensional theory coming from type 2b string theory on some K3, where we have some SCFT sectors with gauge groups gamma I. Then what we can do is that we can reduce this on an S1 to get to a 5-dimensional theory. And this, in this 5-dimensional theory, then these 6-dimensional strings become W bosons of the 5-dimensional theory. And the 2-form symmetry reduces to a 1-form symmetry. And then one can compare with studies of 5-dimensional theories with 1-form symmetries and the effect of these gauged 1-form symmetries there. Furthermore, one can use that this 5-dimensional theory has another F-theory lift, where we explore that there is this second vibration. So we can lift this to an 8-dimensional theory, which is given by F-theory on K3. And this also in 8 dimensions, there are these gauge groups have been observed with these particular 2-form gaugings. So this gives a cross-check via duality of the results that we have obtained. One can, so in 2,0 supergravity, the story is rather constrained. Then we have a unique lattice lambda b, and the 2-form symmetries of the SCFT sectors have to be ADA groups. If we reduce the supersymmetry, then we have more options. So we have different choices for the base for the 2-dimensional manifold that we compactify on. So lambda b is not unique, and in the SCFT sectors we have the same kind of structure. So we will have these they will be specified by these lattices, but these lattices need not be ADA root lattices anymore. There are a wealth of examples that one can construct. So one can look at toroidal orbifolds, and one can look at toric bases. And the reason why I mention these particular examples is that, well, first, we have studied them, and second, because they have been classified, at least in part. So this means that one can do systematic studies of these kind of constructions, and this is something that we are intending to do. Just to give some simple examples, so we can look at a toroidal orbifold example. If we can take a rather simple one, so say we have a 6-dimensional torus, which we quotient out by a Z3 to get an orbifold. Then we can look at this as in F-theory as a compactification where we identify one of these tori as being the F-theory torus, the elliptic fiber, and then the other two are the base. If we do that, then we see that this base here is just given by the orbifold T4 over Z3. And in this base, we have we have 9 fixed points. And if we blow up these 9 fixed points, then we will get what are called non-Higgsable clusters of a particular type. And one can, and these non-Higgsable clusters have, in fact, a 2-form symmetry, and it happens to be Z3 in this case. So this means that the putative global two-form symmetry would then be Z3 to the power 9, because we have 9 fixed points. But what one can show in this example is that it's only the diagonal part here that survives as the gauge two-form symmetry in the quantification. Yes.
5 minutes.
Thank you. That's perfect. So then I have time for the last example as well, which is an example that comes from toric geometry. So here we want to construct a 1,0 example starting from a toric base. So what we start with is F-theory compactification on an orbifold base, which is P2 over Z5. And here I've drawn the fan for this geometry. Now this is a singular geometry. So in order to explore what kind of SCFT sectors we can get, what we do is that we look at the exceptional devices of a minimal resolution of this geometry, and these are drawn in here. And then we read off the gauge groups that are associated to these exceptional devices. So as we blow up these devices, then the fiber also has to be modified. And these gauge groups here is an A4 here, and here we have 2 non-Higgs superclasses again. All of these happen to have Z5 as two-form symmetries. So we get a GS, which is Z5 to the 3. And then to read off what the diagonal Z5 gauging is, so what the gauging is that is reflected by all these light strings, then we can use toric geometry, and we can look at the what we need to find then are the linear relations between these curves. And here I've just given one of these. All the details are of course in our paper. And here from this, what's interesting with this particular relation is that there is a 5 in front of 2 of the terms here. What this shows is that as we blow down these exceptional curves here, then there will be a torsional cycle remaining. And so at the blowdown locus, this particular cycle x1 minus x2 is a torsional cycle. So this will remain as a gauged symmetry. And strings in the setting can then only wrap curves which satisfy this particular relation here, which is exactly what you would see as these constraints on the lattices. So let me conclude. So what I've told you about is that we have 6-dimensional theories, superconformal field theories that are interesting in many respects. And one of their interesting features is that they have global discrete two-form symmetries that are given by certain charge lattices of these theories. And when they are coupled to gravity, these two-form symmetries must be either broken or gauged. And this gauging is only possible if this charge lattice is embedded non-primitively into lambda b. So the lattice, so the SCFT charge lattice must be embedded non-primitively into the charge lattice of the base. We have explored this in different theories. I've told you a bit about 1,0 and 2,0 supergravity here and shown some example. And there is also a duality check with 5-dimensional gauged one-form symmetries that support these results. There is a possibility that this two-form symmetry that appears to be left is broken by other effects. So this is something that we cannot exclude, but we think it might not be. And one reason why we are confident in this is, of course, because we have this duality check. There is a lot of work that remains to be done. So we have only studied this in the geometry description. We have not done a proper field theory analysis and checked the anomaly cancellations, which is needed. And also, I've already alluded to the fact that it would be interesting to classify the allowed two-form gauge groups that one can have in these kind of constructions. So what are the constraints then? So what kind of two-form gauge groups can survive as we put these SCFT sectors together? What we have done in our work is to look at particular examples where we have some control, but there is certainly scope for more systematic explorations. And with that, I would like to thank you for listening.
Thank you for the crystal clear talk, Magdalena. We are running out of time. Maybe we have a time for one quick urgent question. Anybody? Okay, if not, then let's thank Magdalena again.
Thank you.
And switch to Naomi Gendler. I hope I pronounced the name correctly.
It's Gendler with a hard G.
Gendler or Gendler?
Gendler.
Yeah, and as a German, I would say Gendler, but I don't dare to say, because usually you're wrong in this way. Okay, so you're ready?
Yes, let me just share my screen.